So I'm going to talk about somewhat of a niche topic today. It's about hashing design in modern data center networks, its challenges and mitigation techniques. This is a joint work with our colleagues from Texas A&M and Harvard. Today, data center and wide area networks typically employ multipath forwarding. Think about equal cost multipathing, ECMP, or its weighted variant, WCMP. Roughly how the switch hashing works is when a packet arrives at a switch, it's first matched to a next hop group, which is basically a list of ports that you can forward the packet out to that would get it to its destination. The next step, the switch applies a hash function, which then indexes the packet into one of the next hops, and then forwards that packet out of that port. So a good hash function should hash flows equally across all the next hops. When that fails to happen, this is a problem we call hash polarization. And this can happen when you reuse the same hash function or you use correlated hash functions across different switches on the same forwarding path. So let us look at an example. Between node A and node F, there are 4 equal cost paths. So ideally, we want to utilize all of them equally. So when traffic comes into A, it has only 2 next hops to go to. If the hash value of the packet of the packet headers is 0, then you forward it to B. If it's 1, you forward it to C. The problem arises at node B. What if you use the same hash function as A? The problem is then you will only use next hop D because all that green traffic coming into B has hash value 0. And if you're using the same hash function at B, you will not hit E at all. So this is a problem because only 2 out of your 4 paths are used. This is problematic because this leads to poor load balancing, and this tends to result in very high tail latency, which is detrimental to application performance. Like, for example, think about machine learning collective communications, which are known to be highly sensitive to tail latencies. Also, from network operators' perspective, this is just a lot of build bandwidth being unusable because you're prematurely saturating the link. So your usable bandwidth is significantly less than your provisioned bandwidth. So here are our contributions in this paper. First, we formalized for the first time this hash polarization problem. And this is attributed to a lack of uncorrelated hash functions provided in commodity switches. There's a common misconception that random seeds can create uncorrelated hash functions, which are actually not true. And this lack of uncorrelated hash functions become even more acute with increasing adoption of direct connect technologies, topologies. So to mitigate this problem, we had designed 2 approaches. One is, we identified a very common forwarding structure that enables us to reuse hash functions safely. And secondly, we proposed design an SDN-based approach, which does not require any switch modification, to decorrelate switches using the same hash function. Together, our solutions are very near optimal for DCN. And we have reclaimed 33% of network capacity otherwise lost to poor hashing. Let's take a look at Google's data center networks. This is a very typical conventional CLO topology. At Google, due to our skill, this multi-stage CLO comprises 5 stages of switches. This work was first published, revealed in SIGCOMM 2015. With the lower 3 layers of switches comprising what we call the aggregation block, which connects the servers, and the upper 2 layers of switches comprising the spine block, which provides the connectivity across the aggregation blocks. So for interblock traffic, it follows, every single packet follows a fixed structure path, which has exactly A hops, and it goes through the exact same stage sequence. So this suggests a pretty simple hash function allocation scheme, where you basically, for each hop, let's assign a unique hash function. Note that this means for switches at S2, S3, and S4, you will have two hash functions assigned to northbound traffic and southbound traffic respectively. And we call this scheme per stage allocation. Fast forward to more recent years, around 5 years ago, we started building our data center networks using a non-hierarchical direct connect topology. What happens here is we remove the spine blocks and we directly mesh the aggregation blocks together. The problem here, well, first, how do we do routing? So the interblock traffic now either goes over a direct path or it goes through one transit hop. Now, if we use the same per stage allocation, what we're going to see is there's going to be hash collision happening between the source to transit hop and the transit to destination hop. Remember the same hash polarization example that I showed earlier? The problem is at the source S3 switch, you could hash the traffic apart, no problem. But what if only the green traffic arrives at the transit? So now at this you can see my cursor, right? Yes. Let me actually bring it up, the laser. But at this transit S3 chip, unfortunately, you're only seeing green traffic, so you cannot hash it apart. And there might very well be multiple links, equal cost links to the destination. So this is a problem. Now, what can we do? Ideally, if each aggregation block is assigned a unique hash function, then problem solved. But that would require dozens of hash functions at least. But, unfortunately, the commodity switches offer only very limited set of hash functions. And as I hinted at earlier, there's a common misconception that by randomly seeding the hash functions on the switch, you create uncorrelated hash function. That's actually not true. Because the common implementation of the seed is it's concatenated to the input bit vectors, which consists of other packet header fields that you choose to hash upon. So you concatenate a seed to the bit vectors and feed that into the hash function. So the effect of that, roughly speaking, you can find more theoretical proof in the paper. The rough effect of that is it scrambles the next hop, but it does not decorrelate. So what can we do? We have limited hash functions implemented on the switch, hardwired. So you cannot really add new hash functions to it. And then we have a growing need for more hash functions. So we need to find some ways to safely reuse hash functions. And here is one common pattern, which we call color recombination. Again, let's illustrate through an example. Same forwarding graph as before. Traffic coming in, and it's split to green and red, forwarded to switch B and C respectively. We already established that at switch B and C, you cannot reuse the same hash function, right? It's not going to work. So that means we have to use an orthogonal or uncorrelated hash function at node B and C. The result of that is for the next layer at node D and E, now you have traffic coming from both colors, right? So those two colors recombine into your original unpolarized traffic. So now you can actually reuse hash function H. So where do we see this color recombination pattern? It's actually quite prevalent. It's very prevalent in most of the two-stage CLO block design. Remember earlier I showed you the graph of Jupyter topology. You take a Jupyter spine block, for example. You have the S4. It's a two-stage folded GLO. And color recombination, you can basically map this. If you unfold this, it basically looks like the forwarding graph on the left. This allows us to save one hash function at the stage 4 switch. So I can use the same hash function for northbound traffic and southbound traffic. Here's another technique. What I didn't mention earlier was that there are really two hash operations involved in selecting the next hop of a packet. So after a packet is matched to a next hop group, the switch does two things. One is it first applies a hash function, for example, CRC32, which outputs a 32-bit integer. And then the switch modulo that 32-bit integer by the size of the next hop group. And then whatever the remainder is, that's the index for the port that you select. So the nice thing about this is that the group size is completely controlled by the SDN controller. We program them, and it's fully under our control. And we have proved a theorem in the paper which states that if two group sizes are coprime, then the two switches are uncorrelated, even if they use the same hash function. Just to show a very simple illustration, same example again. Packets arriving at switch A, it has two next hops to forward it to. For all the packets that have hash value 0, 2, 4, all the even numbers, it will get to forward it to B. And if you don't do anything at B, well, what happens is they're all going to hit D, and none is going to hit E. But remember the coprime theorem. What if we resize this group to a coprime number, let's say 5? And the way you do that is by just simple replications. Now let's see what happens. Okay, so 0, 2, 4, they're still going to hit D. But starting at 6, you're starting to hit E now. And then this repeats. So now, very nicely, by doing this little trick, you're able to utilize the previously unused path. There's a catch, however, if you're paying close attention. It introduces a slight weight skew. Previously, the intended traffic split is 1-to-1 between D and E, but now due to this replication scheme, the new split is actually 3-to-2. So now you see there's a trade-off existing between the weight precision and how many switch table, ECMP table entries you're going to burn. And we just talked about it, which is expanding, resizing an ECMP group. Co-priming, resizing a WCMP group is a little bit more tricky, and a simple replication may not work very well. So I encourage you to to read the paper about this. Let's see how we apply this co-priming technique in our direct connect DCN network. Again, remember the goal is to decorrelate the transit to destination hop from the source to transit hop. I mean, we could coordinate the group sizes between the two hops to coprime, but we found there's an easier way to do that, which is let's not touch the source group at all. Let's just resize the transit to destination group to a prime number, which in the vast overwhelming majority of the cases should be automatically coprime with the source to transit group. The other benefit of only resizing the transit to destination group is the transit to destination tends to be ECMP, whereas the source to transit tends to be WCMP because of traffic engineering, for traffic engineering purposes. So, and we already said earlier that resizing an ECMP group tends to produce less weight skew without burning too many switch resources. So let's look at some simulation results. In this presentation, we're going to focus on multi-stage closed DCN and the direct connect DCN. You can find more results on ISP networks or general wide area networks in the paper. The hash functions that we use is called RTAC7, which is a Broadcom implementation. It's fairly widely deployed. It consists of a family of 7 hash functions. CRC32, etc. To evaluate the effectiveness of our hashing design, we look at the link utilization across the switches. And we use coefficient of variation to quantify just how much imbalance there is. Also, we do use random seed. So each switch is configured randomly seeded. So let's first look at the closed topology. We compare 2 configurations. The baseline is because of the lack of hash functions, so we will apply the same hash function for both the northbound and southbound traffic S3 chip. And with color recombining, it allows us to allocate, it saves us one hash function at stage 4 switch, which allows us to assign that extra hash function to the S3 southbound traffic. So we compare these two schemes. So here is a representative S3 chip, and we look at its down-facing ports. There are 8 of them. The blue bars show the baseline. You can see that it has a pretty poor load balancing across the links. But when you apply color recombining, the load balancing is significantly improved. We're looking at a coefficient of variation of 0.6 versus 0.05. And because of this, we can increase the effective capacity by 33%. A similar story follows for the direct connect topology. Here we're comparing, again, a baseline where we retain the original group size without copriming, and we compare with our technique of copriming the source group and the transit group. Again, a similar story here. The load balancing performance is significantly improved. Here we're looking at 23% capacity improvement. Next, we explore a little bit the trade-off between the weight skew and the switch table usage. The main takeaways are, and which the results are pretty intuitive as well. By increasing the coprime value from 9 to 73, we're able to reduce load imbalance by 80%. So this load imbalance is purely due to weight skew. But as you increase the ECMP group size, you also burn more ECMP entries. And we also see diminished return after a certain point. Both of these techniques have been deployed in our production for many years now, specifically in the multi-stage CLO topology. We use color recombination, and it's not just in spine block. I would encourage you to think about other places where this is happening, and it doesn't have to be just a single layer due to color recombination. In our direct connect architecture, which is going to come out in this year's SITCOM, we employ both color recombination and copriming. And we have been able to achieve excellent load balancing performance with a coefficient of variation of only 0.03. There's still work remaining to be done. I think for one, hash polarization detection in live networks remains to be a difficult problem. The reason is attributing load imbalance to hash polarization in the face of multiple confounders is actually quite challenging, because there are many things that could impact load balancing. Think about WCMP, traffic engineering, or elephant flow. There's an even harder problem, which is intermittent hashing issues, because due to some coincidental combination of your routing, you might have occasionally good color mixing, which might hide your hashing issue. But when you lose that color mixing, in some occasions, your service may see outages because now your hashing issues start surfacing. So this will be an interesting problem to do more research on. Fundamentally, we believe the way to solve this, as good as the approaches that we have proposed, we believe the fundamental way to solve this is at the switch hardware level, is that we really need the switch vendors to provide unlimited, uncorrelated hash functions and generatable by seeding the hash function randomly. Lastly, I think, how do we automatically detect and discover this color recombining pattern, considering multiple factors like routing, hashing, the traffic entropy, etc. It's also an interesting problem. To conclude, hash polarization is a real yet underestimated problem in production networks. It could reduce reusable bandwidth by as much as 1/3. We have shown you 2 proven approaches to achieve near optimal hashing, and we're actively working with our switch vendors on better switch hashing implementation. With that, thank you all for your attention. I'm happy to take any questions.